Kayda başlıyoruz. Merhabalar arkadaşlar. Bugün dördüncü oturumumuzda dördüncü dersimizi yapıyoruz. Hello, good afternoon, dear friends. Today we are making our fourth session from our Chiang book. We will be starting the chapter 3, Equilibrium Analysis in Economics. So, we will be dealing with equilibrium. But what is equilibrium then? Here we see an old experience, an experiment rather, which has been done during the 17th century or early in 18th century. I guess it's 17th century. And it can be even before. In Germany, it is made in Germany. It is called Magdeburg Hemispheres. Magdeburg is a town in Germany, and there they made an experiment, a physical experiment, to show the effect of the pressure of the air pressure. So the experiment consists of two hemispheres coming together. They make a kind of like a steam cooker. They make a kind of sphere-like object, quite hermetically closed. If you close it, it is like a steam cooker though, and it has a tap in order to make a vacuum in it, to take the air out of this sphere and make a total vacuum, a total empty it from the air. And it has also at each side, it has a kind of small ends, a small something to tie it to the objects. And then they close. It's not a big one. Each hemisphere has a diameter of 50 centimeters, so half a meter. It's not a very big object, and not a very small one though. So when they close it hermetically like this, and then they empty the air from it, these hemispheres stay together. Although they have been, in fact, they were at that time pulled by 4 horses at each side. So together there is a force of 8 horses which try to separate them, but they couldn't. They haven't been able to separate them. So this is the experiment of Magdeburg hemispheres. You see here another, at the right-hand side, we see another. Here you see another version of the experiment. You put the one side of the hemisphere to a kind of somewhere. You just put it fixed, and then to the other end you put a kind of like a balance. You put a tray and you put the weights on it, 1 kilogram, 2 kilograms, etc. And you just augment the weights, and even in quite high weights, you don't manage to separate these spheres, to open this hemisphere, as long as it is filled with without anything. I mean, it's the air is empty. When you fill it again with air, then it opens, and you don't have anything to hold it fixed. Actually, it stays there. It stays closed, thanks to the pressure of the air column above these spheres. So you see this sphere. This is an experiment showing the pressure of air, proving that air has a pressure, and it has indeed a very high, very big pressure. So where is the equilibrium? Here there are many instances of equilibrium. One equilibrium is at each side you have 4 horses which pull the sphere, and if they are equally powerful forces, then this sphere would not move. The forces of the horses from one side will equilibrate, will be equal to the forces of the other, the sum of the forces of the horses at the other side. So you have an equilibrium here. Besides, there is a huge air pressure above the on the surface of the hemispheres of the sphere, but they don't well, they don't break, and they don't get deformed. They don't change their form, but they stay closed. So if the air pressure, if the resistance, there is a resistance of the material of the well, it can be steel, or at that time perhaps it was not steel but something like anyway, a strong metal. And then the strength of the metal, the resistance of the metal resists the air pressure, and it doesn't change its form. It doesn't get deformed. Otherwise, you know that the submarines, for instance, in very high pressures under the sea, they can get pressed, and they can even sink, and they can be crashed. They can crash. They can well, you know, they can be crushed by this water and air pressure above them. But here there is no crash, nothing. There's no deformation. So the resistance of the material, of this metal, equilibrates. It resists, and it gets equal to the pressure of air above the hemispheres, above the sphere. When you put two hemispheres together, you obtain a sphere. So you see, there are many instances, many visualizations of the equilibrium in this experiment. All right, but what is equilibrium in economics? Our subject is economics. So what is the meaning of the equilibrium? 3.1 is the meaning of equilibrium, and we are starting the stationary equilibrium analysis. Why stationary? Because we have the initial and final equilibrium conditions, and they don't well, we don't study, we don't analyze the passage in between. So the equilibrium we will be studying, or the equilibria in plural we will be studying, will be stationary equilibria. We have a very good definition of equilibrium here by MacLab, Fritz MacLab, an economist. The source is here under the page. Well, in the down part, downside of the page, you have the source, the reference. And what does he say, MacLab? He says an equilibrium is a constellation of selected interrelated variables so adjusted to one another that no inherent tendency to change prevails in the model which they constitute. So this is a very good definition, which is not only used in economics, but which can be used in any sciences, any discipline, because it is a very general definition of the equilibrium. So, well, there is a model, obviously. We are modeling things. We are modeling the nature or the society, some social events or some natural events, and there is a model. And this model has variables, exogenous variables, endogenous variables. So dependent variables, independent variables. Exogenous are independent, and endogenous variables are dependent variables. Or explained and explanatory variables. Explanatory variables are rather exogenous, and explained variables are endogenous, which means they find the equilibrium values in their solution values in the model itself, by the solution of the model. So what does the definition say? A constellation, so a set of selected interrelated variables. There are selected variables. That means the modelist selects some variables and doesn't include other variables. So there is a how can I say, there is an aim in the behavior, in the choice of the modelist. So the conception of the models enters the game. Interrelated variables, so they are not unrelated, they are interrelated. So these variables, they come together to form an interrelated and meaningful whole. So adjusted to one another. So they are adjusted. They are in certain positions and not in other positions. That no inherent tendency to change prevails. This means there is not only change, well, the whole situation doesn't change. If it is an equilibrium, it stays for a moment, it stays still, it stands still. The whole thing, the whole situation, the whole position stands still. But moreover, more than this, there is no inherent tendency to change prevails, says McCulloch, which means not only the position of the variables are not moving, they are sort of immovable, or they are in equilibrium, they are not changing, but there is no an inherent, so there is no an inside tendency, motive for these variables to change suddenly from the equilibrium. That just to do the equilibrium to be destroyed suddenly. There is not such an inherent tendency in the model which they constitute. So they constitute a model. These variables altogether constitute a model. You see, each word, each concept in this definition is important. So the conception of the models enters. The specific traits of the model are important to make this equilibrium, to achieve this equilibrium. The position of the endogenous variables, interrelated and selected variables. Endogenous, what is endogenous, what is exogenous, what is the main models, main variables of the model, and what is not, depends on the modelist. It's our choices which define a variable, if it is sort of endogenous or not. So the position of the endogenous variables, not only the absence of change, but even not a tendency to change. You see, there shouldn't be even a tendency to change. Not only that, the variables shouldn't change. And the simultaneous rest of interrelated variables. They should be interrelated. They should not be just standing alone. And chosen variables. So if new variables are added, the equilibrium can be destroyed. If you have an equilibrium situation and then you add some exogenous variables to the model, for instance, all the equilibrium may be destroyed. So chosen variables means this. And if new variables are added to the equilibrium can be destroyed. The model must be analyzed again. Definitely. Very good definition and very, very important points. So there are two types of equilibria. Equilibrium is a Latin word. Equi means equal. Libra means balance. So it is the equal balance, equally balanced. Like the two trays of a two-arm balance. You know, these balances. Equilibria is the equal balance in Latin. Equilibrium is the singular. Equilibria is the plural form. And in English, one uses the Latin words. So the plural of equilibrium is not equilibriums, but one says equilibria with A. So there are two types of equilibria, a goal equilibrium and a non-goal equilibrium. A goal equilibrium is a consciously searched or avoided equilibrium. It's a subject of optimization. We will study these kind of equilibria in chapter 9. We will try to maximize or minimize things, find the maximum, the uppermost points, or the lowermost points, the minima or of these certain things. So this will be a goal equilibrium. For the moment being, we are studying non-goal equilibrium, which is an equilibrium which happens by itself without being a matter of choice. We don't have an aim. We don't try to put the system in an equilibrium position. We just analyze the existing equilibrium of the equilibria of the system, because a system may have more than one equilibria as well. All right, more than one equilibrium, so there it may have equilibria indeed. All right, so we start with a partial market equilibrium, a linear model, one of the simplest models in economics. It is the chapter 3, subheading 3.2, partial market equilibrium, a linear model. We are starting with a linear model, and we will see non-linear models as well. What is the solution of a model to solve a model? It is finding the set of values of the endogenous variables of the model in terms of the exogenous variables, so as to satisfy the equilibrium conditions of the model. You see? So we will find the values of the endogenous variables, the equilibrium values of the endogenous variables, which put the model in equilibrium. And these values will be expressed in terms of the values of exogenous variables. So on the left-hand side, we will stay with only endogenous variables, and on the right-hand side, only exogenous variables. This will be the solution, and satisfying all the conditions of the equilibrium. So first, constructing the model. Let's construct the model, the simplest economic model we will see in this term. Each model has assumptions. We build the model according to some assumptions, building it upon some assumptions. And those are, there is only one homogeneous good, and one homogeneous good. You can't make the difference from this good to the other, to the next one. Like, for instance, oil, petrol, the oil, gasoline, or normal oil, the cooking oil, whatever, or water. You can't say this water is different from the other one if it's not bottled, or if it's not whatever. Electricity. You don't make a difference between the first kilowatt hour and the second kilowatt hour of electricity. It is the same. You know, it's a homogeneous good, isn't it? But it has, though, when you study thoroughly, when you study deeply, you can find some differences as well, but we don't notice them. We don't observe them usually. So the assumptions, which are simplifications, of course, of the reality, there is only one homogeneous good, only one isolated market. In real world, no market is isolated from another one. All the markets are interrelated. But here we assume that there is an isolated market. And there are homogeneous producers and consumers in this market. There is no monopoly power. There is no difference. There is no brands, fashion, whatever. All the producers produce one homogeneous good, and all the consumers, they consume one homogeneous good, like the water from the tap or the electricity we buy. All right. And all the electricity, let's call it, is produced by this. It can be many producers, but they produce all with the same technology in the same way. They don't make a difference between producers neither, and consumers don't have different tastes. They have the same taste. They just want to use this electricity. That's all. You see, very simplified. It is unrealistic though, but we have to simplify to analyze, and then we will add some more sophistications through time. What are the endogenous variables of the model? QD, Q sub D, it's quantity dependent of the good. For instance, in kilograms or in kilowatt hours, whatever. QS is the quantity supplied of the good. This one is in kilograms as well, or in kilowatt hours, and whatever, in liters, if we buy water, in gallons, whatever. P is the price of the good. This is expressed in Turkish liras or American dollars or whatever, euros, whatever, Japanese yen, whatever currency you use in this country, in this region. So those are the endogenous variables of the model. We have quantity demand, quantity supplied, and price. 3 endogenous variables. Exogenous variables can be many, but here we have only the coefficients. It's a very simple model, so we have only the coefficients which are exogenous. Equilibrium condition, which is an equation, in fact, an equilibrium condition is a type of equation. It is QD equals QS, meaning the quantity demanded of the good at the end of the day, the quantity demanded of the good should be equal to the quantity supplied of the good. Quantity supplied is what the producer or the seller brings to the market. Quantity demanded is what we want to buy. And if we agree upon a price, we buy everything that the market offers, the supplier offers. So there are many suppliers, many customers, many consumers. We come together at the market. Market is a medium. It can be a real market or an imaginary sort of artificial market like internet. And everybody, I mean, all the sellers, they give a price. All the buyers, they want a price. And if they agree upon a market price, upon an equilibrium price, indeed, all the goods, commodities brought by the sellers, by the suppliers, will be bought by the consumers, and everybody will go home happily, you see. So, and we have two, oh, here I just skipped, I have been sort of, I haven't made attention, and here these things have stayed in Turkish. Davranışsal denklem means behavioral equation. Those are behavioral equations. I will correct it in the presentation and put it at the page of our class, of our lesson, and I will also send you. I will just correct this. In English, it is behavioral equation. Davranışsal denklem in Turkish is behavioral equation. So we have two behavioral equations in this model, the demand equation and the supply equation. The demand equation is quantity demanded equals A minus BP. P is the price. A and B are positive coefficients. What does it mean? There is a demand, a quantity demanded of the good, irrespective, not regarding the price. Whatever be the price, even when it is zero, for instance, when the price is zero, minus BP is zero. So QD equals A. This is a constant value, which means there is perhaps a highest value, a highest quantity of this good, which people would buy, even if the price is zero. This is not infinity. So even if the price of the apple is zero, how many kilograms would you just take from the market? Would you get from the market? Perhaps 10 kilograms. You don't get more than this. So if 100 people gets 10 kilograms each, 100 people get 10 kilograms each, then it will be 1,000 kilograms, a ton of apple. So this is, if the price is zero, if the apple is distributed freely in this market, there is also an upper limit. It can be very high, but there is it's not infinity. When the good is distributed free, people demand a certain quantity. This is A. This is called autonomous demand. And there is also a demand depending on price, minus BP. And this is correct. Why? Because when the price augments, B is positive, minus when we have minus at the front, then it means it means QD, quantity demanded, and the price, they vary inversely. They are in inverse proportion. And this is very realistic, because when the price of a good augments, the quantity demanded of the consumer, what we want to buy, diminishes. When the price diminishes, our quantity demanded augments, so they are inversely proportional. This is realistic. At the supply equation, which is also a behavioral equation, we have QS, quantity supplied, equal to minus C plus DP. C and D are positive, so minus C is negative, plus D times P. There is also an autonomous sort of supply, but this autonomous supply is negative. When the price of the good is zero, the seller doesn't want to sell. It wants to buy. That's why this coefficient is negative. Minus C. C is positive, minus C is negative. the price should attain a certain level before the supplier wants to supply, to produce and to sell this good. Otherwise, he or she wouldn't sell this good, would buy rather if it's too, if the price is too low. If the price of the, for say, cheese is 50, well, when the normally cheese is, let's say, 200, 300 liras a kilogram, if the price of the cheese, same quality of cheese, is 50 liras, the seller won't produce, won't sell, he or she would buy it rather. He would become a buyer, a consumer. So this minus C means that if when the price is 0, the seller doesn't sell but buys rather than selling. And DP plus DP is also realistic because the quantity supplied, what the quantity that the producer wants to produce and sell, is proportional with the price, because when the price augments, its willingness to produce and sell augments. When the price diminishes, when the good becomes cheaper, the producer or seller doesn't want to sell much. So this is realistic as well. A is called autonomous demand. That's to say the quantity demanded if the price of the good becomes 0, that is, if it is given free. Minus C is autonomous supply. That is, if the price of the good becomes 0, the supplier does not sell but becomes a buyer, as we explained. And C over D, we can also derive from this equation the minimum price that the producer wants to produce. It is QS is 0, minus C passes to the other side, and divided by D, we obtain P minimum, which is C over D. This is the minimum price for which the commodity starts being supplied. We can obtain it by putting QS equals 0 in this equation. All right. Then, here we have the diagram of this, the Cartesian on the we have the Cartesian coordinate system as we studied before, and here the supply and demand of this good and its equilibrium is depicted on this diagram. On the x-axis, the horizontal axis, we have the price. On the vertical axis, the y-axis, we have the quantity demanded and quantity supplied, the quantity. This is a normal, or well, normal. It's a mathematical demand and supply function. In the economics books, we encounter rather we put the price on the vertical axis and quantity on the horizontal axis. This is the inverse demand function. Why do we do so? Because first it's a tradition, and besides the price is the average revenue. The demand curve or the demand line, this diagram, shows also the average revenue of the sellers. That's why it is preferred in the economics books, it's preferred to put the price on the y-axis and QS, the quantity, on the x-axis. But in mathematics, we use also the normal demand function, which is not the inverse demand function, but the normal demand function, where we put price P on the x-axis and quantity on the y-axis, on the vertical axis, you see. And, well, quantity demanded, the demand equation, is depicted by this line. How? When the price is 0, we have the origin, 0 point, where the price and quantity are 0. So when the price is 0, the quantity demanded starts by A. This is the highest quantity. Of course, the price and quantity are also positive, positive measures. We don't know what a negative price is or negative quantity is. In economics, at least at this level, negative price and negative quantity doesn't have any meaning. An apple cannot be a negative, and the price of an apple cannot be negative. Nobody gives you apples and money besides, in addition to apples. You give money and you buy apples. So there is a positive price. And if it is distributed freely, the price is 0. It can't be negative. And negative apple, I haven't seen a negative apple up to now. So the quantity of apples and the price of apple are both positive. So we are working at the first quadrant, where both price and quantity, both x and y, are positive, isn't it? So The quantity demanded, the equation of the quantity demanded is QD equals A minus BP. When P is 0, QD, quantity demand, is A. This is the maximum quantity that people want to get to buy when the price is 0. Then when P becomes positive, this quantity demanded diminishes with price. From A, it diminishes, and minus B is the slope of this line, as we will learn when we learn also the derivatives. The quantity supplied, on the other hand, is minus C plus dP. So when P is 0, when the price is 0, it starts from minus C. And at this region from minus C to, when the price is from 0 to C over D, which is the minimum price, the seller wants to start selling. So the producer wants to start producing. This region is imaginary. There is no transaction here. There is no supply here. This is, the supply is a negative demand actually. Here there is demand, there is no supply. When the price is over C over D, the supplier, the producer or the seller, starts selling, starts supplying. So minus C plus dP, here we have an increasing curve, the line rather, because it's a linear function. Qs is minus C plus dP, and it augments with price. So you see, both the demand and supply behaviors are depicted with these lines. It is a very simple model, but it also sort of tells us things. We can make some analysis with this. And D is the slope of this supply line. If it is curve, it will be supply curve. If it is line, it will be supply line. And this is demand line. And when they cut each other, when they intersect, it means the demand equals supply. This is the equilibrium. In economics, we see this demand, supply and demand, they cut each other at one point, at the equilibrium point, where we have when we take the projection of this point over the price axis, P axis, we obtain the P star or P bar in the book. I prefer P star or PE from equilibrium. In the economics book, you can see PE, QE as well. So this is the price where the quantity demanded and quantity supply are equalized, and we obtain one equilibrium quantity, which is quantity star or quantity Q bar, Q star, or QA, as you wish. So this P star, Q star, or PA, QA, or P bar, Q bar couple means it is the equilibrium of these endogenous variables. It's the equilibrium position. So this is the equilibrium, is a couple, is a pair, P star, Q star, you see. So this is figure 3.1 in our book. How can we solve this model? Well, we can solve it by elimination of variables, by replacing variables with their exogenous values or whatever. So this is the simplest way of solving a model. We replace the behavioral equations in the equilibrium condition. What is the equilibrium condition? QD equals QS. Q sub D equals Q sub S. Quantity demanded equals quantity supplied. And if we call this quantity Q, it will be the equilibrium quantity. So Q will be equal to both A minus BP and minus C plus dP, because they are equalized at the equilibrium condition. So we replace A minus BP instead of QD and minus C plus dP instead of QS in the equilibrium condition. What do we obtain? A minus BP equals minus C plus dP. So P, you see Q's disappear. What do we have in end? P. The only variable which remains is P, the price. So we put all the price variables with their coefficients to the left-hand side, and all the coefficients standing alone, all these exogenous coefficients, exogenous variables, to the right-hand side. Endogenous ones to the left-hand side, exogenous ones to the right-hand side. Here it made the inverse. It collected all the prices at the right-hand side, but it's the same thing. It doesn't make a difference. Usually one puts all the endogenous variables to the left-hand side and all the exogenous variables to the right-hand side. But we can also put all together, I mean all the prices together at the right hand side, and all the exogenous ones, the coefficients, at the left hand side. The book made like this. So A plus C, when we put minus C to the other side, it becomes plus C, you know. And when we put minus BP to the right hand side, it becomes plus BP. So here we have A plus C equals BP plus DP. And when we factorize P, then we have, when we take it as a product, as a factor, then we obtain B plus D times P. So A plus C equals B plus D times P. And when we divide both sides by B plus D, we obtain P star, which is the equilibrium price, A plus C as A plus C over B plus D. This is the equilibrium price, solution of the price of the model. And it is expressed in terms of only the exogenous coefficients. You see, here we don't have any more endogenous variable. We have A plus C over B plus D, all exogenous coefficients. So this is the solution and the equilibrium price of the model. And B plus D, which is a denominator, should be different from 0. Why? In order this expression to be determined, to be defined. Otherwise, it's undefined, it's indeterminate if B plus D is 0. But what does it mean? Geometrically and mathematically, what does it mean that B plus D is 0? Alright, the denominator should not be equal to 0. But what does it mean? It means, let's go back to the picture. It means B and D minus B is the slope of the demand line, and D is the slope of the supply line. If B plus D is 0, it means minus B equals D, or D equals minus B. It means the slope of these lines are equal. So this means that these lines are parallel to each other. They don't intersect, so they intersect in the infinity. That's why we don't find an equilibrium if B plus D is 0. Or they can be one on the other, which are also parallel, but then we have all the points which are equilibrium, which is nonsense as well. You see? So the first thing is this: B plus D should not be equal to 0. Another condition is that A, B, C, D are all positive, so the equilibrium price is A plus C plus B over B plus D. Two positives sum together make a positive, and two positives sum together make a positive quantity. So positive by positive is positive. So P star is positive as well. Then we can accept it as a price. We can interpret it as a price because the price cannot be negative. So at this level, at least, when you go to the master's or PhD doctorate level, perhaps you can encounter some negative price and negative quantities, but this is another thing. It's not apples and prices of apples. All right. So what do we have else? We have the Q star, which is the equilibrium quantity. How can we solve the equilibrium quantity? It's simple. Once we have the equilibrium price, we can replace it in one of the behavioral equations. We can replace it in the demand equation or the supply equation. Here it is replaced in the demand equation. You can also try with supply equation. You will obtain the same thing. What do we do? QD star, Q star, which is quantity, equilibrium quantity, is equal to equilibrium quantity dependent, QD star, and it is equal to A minus B P star. When we replace P star here, we obtain the equilibrium quantity. What is P star? A plus C plus over B plus D. So what we obtain is A minus B times A plus C over B plus D. And when we put these in the same denominator, B plus D, we obtain A times B plus D minus B times A plus C over B plus D. When we distribute these multiplications inside parentheses and simplify, let's see, AB plus AD minus BA minus BC. And at the denominator, B plus D. You see, AB plus AD minus BA. AB and BA are the same, so minus BA. AB and minus BA, they cancel each other. we are left with AD minus BC at the numerator. And at the denominator, we have B plus D. So the quantity, equilibrium quantity, is AD minus BC or B plus D. Here again, B plus D should not be 0, and all these things should be positive. AD minus B should be 0, and B plus D should be 0, so that we obtain Q star greater than 0. The quantity should be positive as well. You can also obtain AD minus BC negative and B plus D negative all together, negative. So negative by negative, negative divided by negative would be positive again, as well. And this is possible also as well. And this is acceptable. AD greater than BC is necessary for Q star to be formed at the first quadrant. That's true. If B plus D is positive, then AD minus BC should be also positive, which means AD should be greater than BC. Another way of representing the solution, the equilibrium, is this. We can represent the equations by sets. D, the set D, is the set of PQ pairs. Both are elements of the R square, real numbers by real numbers. That means both P and Q should be real, so that Q equals A minus BP. You see, we can also represent this equation by a set. And what is the supply? Supply is also a set of PQ values, price quantity pairs, all element of R square, which means all are real numbers, so that Q equals minus C plus dP. You see, D is the demand equation, S is the supply equation, represented as sets. And what is equilibrium? Where these two sets intersect, the intersection of D and S. It is P star, Q star. One point here. It can be many points as well if the equations are not linear. All right. So here we are at 3-3, partial market equilibrium, a nonlinear model. Here we have 14 slides actually, so we will finish also the 3-3. We will come up to the end of 3-3, and we will solve the exercises and then control them from the solution book I gave you. All right. 3-3 is partial market equilibrium, a nonlinear model. Now we will learn how to solve the nonlinear models. The behavioral, well, we have also the first equation, which is the equilibrium condition, QD equals QS, quantity demanded equals quantity supply. The second and third equations are behavioral equations. Second equation represents the demand behavior, which is QD equals 4 minus P square. You see, this is a square equation. This is a square function. It is not linear. And 3 is the quantity supplied. It is 4P minus 1. This one is linear. Minus 1 plus 4P if you wish. Here minus C is minus 1. C is 1 here. So minus C is minus 1. You can write down as well, if you wish, minus 1 plus 4P or 4P minus 1. It's the same. So when you put 2 and 3, the equations, the second and third equation in the first one, when we replace them, what do we obtain? Instead of QD, we put 4 minus P square. Instead of QS, we put 4P minus 1. So 4 minus P square would be equal to 4P minus 1. And when we put all these things on the on the right-hand side first, and then we can put it on the left-hand side, or we can put all together on the left-hand side and multiply the whole by minus 1. It is the same. We obtain, if you take this minus P square to the other side, it is plus P square plus 4P, and here we have 4. When it passes to the other side, to the right hand side, it becomes minus 4 minus 4 minus 1 minus 5. So altogether we obtain P square plus 4P minus 5 equals 0. You see, 0 equals P square plus 4P minus 5, but it is symmetric, so we can just change the places, and we obtain P square plus 4P minus 1 minus 5 equals 0. All right, this is the equation we have to solve in order to find the equilibrium price. But how shall we solve? So the first thing is to note is that quadratic equation versus quadratic function. A quadratic function, which is p squared plus 4p minus 5, for instance, it cannot be solved. There is not a solution of a function. There are solutions of equations. So this function should be equal to something, equal to 0, for instance, in order to be solved. So when we equalize, when we put this function fp, p squared plus 4p minus 5 equal to 0, then we obtain a quadratic equation. Why quadratic? It is in square. Quadratic means in square. Quadrat is square in Latin. So quadratic equation is in square, in second degree equation. So a second degree function, and when we put it in equals to 0, it becomes a second degree equation, a quadratic equation, and it can be solved. It can be solved graphically. For instance, if you have p squared plus 4p minus 5 equals 0, you may draw it on paper or make it draw by a computer on the Cartesian coordinate system, PQ axis, PFP axis rather, not PQ but P and FP axis. FP is this function. So if you draw this function like this, and if you see where it is equal to 0, it means where it cuts the x-axis, the p-axis, you obtain 1, 0 and minus 5, 0. So for p equals 1, you obtain fp equals 0, and for p equals minus 5, you obtain fp equals 0. But depicting is not always easy, and it's not a practical method, so we need a general method for solution. For instance, here you have p squared plus 4p minus 5 equals 0. If you try 1, as a candidate, if you try p1 equals 1, p1 star, 1 times 1 is 1, plus 4 times 1 is 4, 4 plus 1 is 5, minus 5, 0. So 1 is a root of this equation, meaning a solution of the equation. So p1 star is 1. Another solution is minus 5. We see it from the graph, or we can calculate by trial and error, or with the other methods we will learn now. So if we try minus 5 times 5 times minus 5 is 25. Minus 5 times 4 is minus 20. Minus 5 minus 25. 25 minus 25 is 0. So P2 equals minus 5 satisfies the equation as well. This is a solution. So we can also put this in one of these demand or supply equations. 4 minus 1 is 3. So P1 Q1 star, or P1 star Q1 star, P1E Q1E, first equilibrium is 1, 3, where the price is 1 and quantity is 3. And the second equilibrium is minus 5 times minus 5 is 25. 4 minus 25 is minus 21. So we obtain P2 Q2 star, or P2 equilibrium Q2 equilibrium, minus 5 minus 21. And of course, we accept the first one, P1 star Q1 star, the first equilibrium, but we discard the second equilibrium because the price and quantity are negative. We don't accept negative prices or negative quantities. Here both are negative. Even if one were negative, we would have discarded it again. So P2 is less than 0 and Q2 is less than 0. They are negative, so they are economically meaningless. We find the solutions, we find also the negative solutions, but then we say that they are economically meaningless. This is important. You see? All right. So here we come to the general solution of these quadratic equations, the quadratic formula. What is it? When we have in hand an equation like ax squared plus bx plus c equals 0, a being different from 0, of course, otherwise we have a linear equation. This is a quadratic equation, so a can be positive or negative, but it should not be 0, of course. Then its two roots can be obtained from the quadratic formula. This is the quadratic formula. x1 bar, x2 bar, or x1 star, x2 star, x1 equilibrium, x2 equilibrium, x1e, x2e, as you wish. You can name it one of these. And then it is equal to minus b. Here you have a, b, c, the coefficients of the equation of the, ax squared plus bx plus c. So the solution is minus b plus and or minus square root over 1 over 2 means square root. Square root of b square minus 4ac, the whole over 2a. This is the formula of the solution of a quadratic equation, of second degree equation. ax squared plus bx plus c equals 0. And it is easy to use. Perhaps you have seen it before as well. You have used it before as well. But now we will prove it as well. Why and how can we obtain this solution? This solution works. Sometimes you find real values. Sometimes you find positive values. Sometimes you find negative values. Sometimes you find real values. Even sometimes you find imaginary values, complex numbers, complex values. But you find always some value. It solves the this formula solves the quadratic equation. All right. The minus b plus part gives one solution, minus b minus part gives the other solution. So each time you obtain two solutions. Sometimes these two solutions can be equal. You obtain one solution by both sides as well. So let's prove it and see that it's really the thing, the solution. Here we will use a trick which is called completing the square. We will complete the formula to a whole square. How do we do it? We do this way. First, we divide the whole equation, the left-hand side and the right-hand side, by a to obtain. When we divide the whole equation by a by a is 1. So here we are left with 1x squared, which is x squared, plus b over a times x plus c over a equals 0. So when we divide both sides of this equation by a, we obtain this equation. All right. Then we subtract c over a, which means we add minus c over a to both sides. So c over a minus c over a disappear, they cancel each other, and here at the right hand side we are left with minus c over a. At the left hand side we are left with x squared plus b over a x equals minus c over a. Great. Then it makes one more thing, this book. It adds to both sides of the equation b squared over 4a squared. We will see shortly why it does so. Because we need a term to complete the whole thing to a complete square, to a whole square. This is b over 2a squared. You could have seen it with a little bit exercise, with a little bit sort of experience. You could have seen it. But anyway, so we have x squared plus b over ax equals minus c over a. And when we add b squared over 4a squared to both sides of this equation, we obtain x squared plus b over ax plus b squared over 4a squared equals to, here, minus c over a plus b squared over 4a squared. Or if you wish, plus b squared over 4a squared minus c over a. You see? It's not so difficult. So since we added the same quantity b squared over 4a squared, the same term, to both sides of the equation doesn't change. It is the same equation still, but we inserted a term. This is a very much used trick in mathematics. If you want to insert a term in an equation, you either add it or add it and subtract it, or you add or you multiply with this equation and divide with this equation at the same time, so that you multiply by 1 the whole thing. Or when you add and subtract the same thing, which means you add 0, so you don't change the equation. And here, instead of adding and subtracting b squared over 4a squared to one side, we added b squared over 4a squared to both sides. So it doesn't change the equation either. So we have still the equality here. Great. So what do we have now? We have at the right hand side b squared over 4a squared minus c over a. We can put it in the same denominator by multiplying this minus c over a by 4a. Then we obtain b squared minus c times 4a minus b squared minus 4 times ac, the whole over 4a squared. The right hand side is this. And what we obtain at the left hand side, you see x squared plus b over ax plus b squared over 4a squared. But this is a complete square. This is a whole square. It is the square of x plus b over 2a. If you don't believe me, then you can just multiply. You can just open this a plus b square, which is x plus b over 2a square. X square plus b square over 4a square, which is here, and 2 times the product of them, 2 times bx over 2a. To simplify, we obtain b over ax. You see, this is really, I mean, x square plus b over ax plus b square over 4a square is really x plus b over 2a in square, the whole thing in square. So this square at the left hand side is equal to b square minus 4ac over 4a square. Great. We need x plus b over 2a. If we take the square root of this term, we obtain only the positive root, not the both sides. Because, well, the square root of 4 is 2, all right. But what is the x which gives us, when squared, when multiplied by itself, which gives us 4? It is both minus 2 and plus 2. When you multiply minus 2 by minus 2, you obtain 4. When you multiply 2 by 2, you obtain 4 as well. So if we have here the parenthesis square, then the x plus b over 2a will be equal to plus or minus of this equation, of this expression, and the square of this expression. So what we obtain here is x plus b over 2a equals plus or minus square root of b square minus 4ac or 4a square. But 4a square the square root of b square minus 4a square, 4ac over 4a square. Square root of the whole thing can be also divided in square root of the numerator and square root of the denominator. But 4a square is already positive, so I can take it as 2a. Since I take here already the plus and minus together, I already obtain plus and minus 2a. But here I have to obtain the square root of b square minus 4ac. So here we have plus or minus square root of b square minus 4ac over square root of 4a square. But then we can just say this is plus or minus square root of b square minus 4ac over 2a. It doesn't change because we have already have plus or minus. So we include all the possible cases. But here we have b over 2a. Let's subtract let's add minus b over 2a to both parts, or let's subtract b over 2a from both parts. So we obtain x equals b over 2a minus b over 2a. b over 2a's cancel each other. We are left with x. On the other side, we have minus b over 2a plus or minus square root of b square minus 4ac over 2a. So we obtain really this expression. x1, x2, x1 bar, x2 bar, or x1 star, x2 star, or x1e, x2e for equilibrium is equal to minus b plus or minus, because here we have minus b over 2a, which has the same denominator. So we can put all together in same denominator and say minus b plus or minus square root of b square minus 4ac over 2a. You see, we proved we obtained the same expression. So this is correct, this formula. All right. So when we apply this formula to our problem, which is p squared plus 4p minus 5 equals 0, we want to obtain an equilibrium price out of this equation. So a is 1. P squared is multiplied by 1 here. So a is 1, b is 4, and c is minus 5. Let's form the, you see, a is 1, b is 4, c is minus 5. And x is p in this case. The unknown is p. So we'll find p star. P1 bar, P2 bar as the book says, or P1 star, P2 star, or P1 equilibrium, P2 equilibrium if you wish. We obtain two equilibrium prices. So what is it? Minus b, minus 4, plus or minus square root of b square, which is 4th square, which is 16, minus 4ac, minus 4 times 1 times minus 5. Minus 4 times 1 is minus 4, times minus 5 gives 20. So here we have 16 plus 20, the whole squared. Square root of 16 plus 20. And then the whole thing is divided by 2 times a, which is 2 times 1, 2. Great. 20 plus 16 is 36. The square root of 36 is 6. Here we have minus 4 plus or minus 6 over 2. So minus 4 plus 6 is plus 2 over 2 is 1. Minus 4 minus 6 is minus 10 divided by 2 is minus 5. You see, we obtained the two equilibrium prices. One is 1, the other one is minus 5. And of course, we will say minus 5 is meaningless, economically meaningless. We will take this one as a solution. Although minus 5 is a solution as well, but it is not acceptable economically. It's not meaningful. It's meaningless, economically meaningless. You see? All right. So another graphical solution, we can also have another graphical solution. Of course, I will not make you draw these graphics. Our exams, our exercises will consist of solving problems, not depicting graphs. Anyway, drawing graphs. But here we have some another solution by graphs. So we can depict both the demand and supply curves on the same axis. Here axis, you don't see the axis for some reason, they disappeared. Here we have the x-axis and here we have the y-axis, the horizontal and vertical axis, and the demand curve, this time is a curve, it is a parabola. It is the q equals 4 minus p square. When you depict it, you obtain this parabola, which whose arms are they go to minus infinity. This is 4 minus p square. And for the supply, we obtain 4p minus 1. It starts by minus 1, and then it goes up with a slope of 4. This is 4p minus 1, a line. And they cut each other in 2 points. One is 1, 3 here, where the price is 1 and this quantity is 3. The other one is minus 5 minus 21. When you put these prices in the quantity demand and quantity supply, you can also find the quantity, equilibrium quantities, which is 3 for the price 1 and minus 21 for the price minus 5. And when you see where they cut each other, this line and the curve, you also find minus 5 minus 21 and 1, 3. And we accept, of course, this 1, 3, the solution where both price and quantity are positive. But we also find this solution, and we see that it is economically meaningless. You see? And their intersection is 2 points. One is 1, 3. The other one has coordinates minus 5, minus 21. So this is the solution set of this problem, this equation. All right. So what do we do with if we have higher degree polynomial equations? This is possible as well. There are not only quadratic equations, but we can have third degree, fourth degree, fifth degree equations, etc. So how shall we solve them? The solution is factorization. To put them in factors, in products, factorization. So how do you factorize, for instance, an equation like this? X to the power 3 minus x squared minus 4x plus 4 equals 0. Well, here it is easy. From the first two terms, we can take x squared to the factor, and then we remain with x minus 1. So the first two terms give us x squared multiplied by x minus 1. And from the two ending term, to sort of the third and fourth terms, we can take into factor minus 4. Then we are left with x minus 1. So the whole thing, this three third and fourth terms, give us minus 4 times x minus 1. So we have x squared times x minus 1 minus 4 times x minus 1. We take x minus 1 in factor, and we obtain x minus 1 times x squared minus 4 equals 0. You see, all that time this is equal to 0. It doesn't change. We just factorize. Then x squared minus 4 is, as we know, x minus 2 by x plus 2. So the whole thing is factorized in x minus 1 times x minus 2 times x plus 2. And the whole thing is equal to 0. What does it mean? If the whole product is 0, each one of these factors should be 0 one by one. Or x minus 1 is 0, or x minus 2 is 0, or x plus 2 is 0. So from these three sub-equations, x minus 1 is 0, x minus 2 is 0, or x plus 2 is 0, we obtain three solutions. If x minus 1 is 0, x1 star is 1, x minus 2 is 0, x2 star is 2, and x plus 2 is 0, then x3 star is minus 2. You see, this way we obtain the three solutions of this equation. Then, well, we can use some trial and error to find some roots, but there are also some ways for these trials and errors. Generally, an nth degree polynomial equation would give n roots. Some of them can be the same root and even an imaginary root, of course, if the coefficient of the nth term, the highest term, with the highest degree is 1. That is, if it is different from 1, it can be done equal to 1 by dividing both sides by that coefficient as well, of course. If the coefficient of the highest term is equal to 1, the constant term will be the product of the roots. This is also a theorem, we will see. So, at the theorem 1, we have x to the power n plus a n minus 1 x to the power n minus 1 plus a n minus 2 x to the power n minus 2, etc. up to plus a1 times x plus a0 equals 0. This is a polynomial equation. Here we have a polynomial function equals to 0. This is a polynomial equation starting by the highest term and ending with the constant term. And the highest term has the coefficient 1. All right. So, if a polynomial equation has, of that type of course, has all the coefficients as integer numbers, and if the coefficient of its higher degree term is 1, as it is here, and if it has integer roots, these are the factors of the a0 or divisors of the a0. So we will take the integer factors, divisors of a0, and search for the roots of this equation in the divisors, in the factors making this, a0, the prime numbers, the prime divisors of a0 rather. But we should try both the positive and negative divisors. So the proof of this theorem: if an equals 1, this polynomial can be factorized as x minus x1 times x minus x2 times x minus x3, etc. times x minus xn. You can always factorize this polynomial as x minus a root times x minus a second root, x minus nth root equals 0. The first term will be a product of n times x by itself. So here we multiply x by itself n times. You have n factors just like this. So we multiply x by itself n times, which is x to the power n. Then we obtain all the intermediate terms like this, multiplying, and the nth term, the constant term, would be a product of all these x1, x2, xn, all these roots. But depending on how many factors you have here, it can be minus or plus. Because if you have odd number of roots, odd number of factors, then you will have a minus sign at the head of this product of roots. And if you have a even number of products of factors, then you will have a plus at the head of these, the product of these factors, of these roots, from x1 to xn. So the first term will be a product of n times itself, let's say x to the power n, as we see, and the product of the negative roots, minus x1 to minus xn, will give the last term, that's a0. But it's not guaranteed that all the roots will be integer. This is the problem. We should be able to find some integer roots and factorize x minus this root, x minus x1, and so on. There is also a polynomial division. I don't know whether you have come across to it. Otherwise, we can also make together. It's not necessary, but we can use it. There's a method called polynomial division, like the normal division, but it is done with polynomials, which can be used for factorizing polynomials. So if an equation, for example, if an equation such as x to the power 4 plus 5 over 2 x to the power 3 minus 11 over 2 x to the power 2 minus 10 times x plus 6 equals 0 is given, well, here we have fraction coefficients. The coefficient of the highest term, x to the power 4, is 1. But these fractional coefficients can disturb us. In this case, we can multiply the whole thing by 2, the whole equation by 2. Then we obtain 2 times x to the power 4 plus 5 times x to the power 3 minus 11 times x to the power 2 minus 20x plus 12 equals 0. Sometimes it is easier to work this way, or in other times it's better to leave the coefficient of the highest term as 1 and try to see some fractional roots from these fractional coefficients. Sometimes it's easy, sometimes the other way around. So what does the theorem, what is it? Yeah. Why don't we have some exercises here? I should add some exercises here, I guess, if there is in the book. Anyway, so the second theorem says, here we have an to the x to the power n plus an minus 1 x to the power n minus 1 plus, here there's something, I don't know what, it doesn't matter. Here we have some dot dot dot. It continues like this, and plus a1 times x plus a0 equals 0, the usual polynomial equation. But this time, in front of the x to the power n, we have an. The coefficient of the highest term is not 1, but an. So this is a polynomial equation with integer coefficients, and that it has a rational root, which is the quotient of two prime numbers such as r over s. So here we have an equation, an polynomial equation with the coefficient of the highest term different from 1. It's an. Here we can probably, this equation would have some fractional roots. Some solutions as fractions. And how shall we know it? Where shall we look it for them? So here these roots, fractional roots, will have the form r over s. The r's we will look at in the prime divisors of the a0, and the s's for the s candidates for s, we will look at the prime divisors of an. Why? Because if for obtaining 1 here, we can divide all the equation by an. So at the denominator we have an, at the numerator we have a0 at the last term. So if we have some rational roots, if this equation has some rational roots, we should rather look for them at the prime coefficient, prime divisors of a0 by prime divisors of an, so r over s, you see. Let's see an example. Are there rational roots of a fourth degree quartic polynomial of the form 2 times x to the power 4 plus 5 times x to the power 3 minus 11 times x to the power 2 minus 20 times x plus 12 equals 0? So a0 is 12 in this case, and an is 2. So we should
first factorize them, each one at its side, and then form this R over S fractions. 12. What are the factors of the not the prime but the integer factors of 12, the divisors of 12, both positive and negative ones? 1 minus 1, 2 minus 2, 3 minus 3. 12 is divisible by 1, 2, 3, 4, 6, and 12 by itself. So we have to take all these divisors, positive and negative. 1 minus 1, 2 minus 2, etc. up to 12 minus 12. And then for an equals 2, we have possible candidates. 1 minus 1, 2 minus 2. Those are the divisors of 2. 2 is a prime number, so it is divided by itself and by 1. And also the negative ones. We can take the negative divisors. And then try the R over S fractions, like 1 over 1, 1 over minus 1, minus 1 over 1, which is minus 1 again, 2 over 1, 2 over 2, 3 over 2, 3, etc., etc. And this is a informed way of trial and error, of course. We can't just guess which one it is. We have to try and make errors and find the correct ones. And if we find one correct one, then we can factorize it and try to diminish the degree of the equation and so on. Here in this way, 4 successful roots by trial and error: 1 over 2, 2, minus 2, and 3. As an exercise, you can put these values in this equation and see that they all give 0. They are really roots of this equation. And besides, what do we have here? Oh yeah, when we divide both sides of the equation by 2 and factorize it, that is this equation, the previous equation, this one. If we divide both sides by 2, then we obtain x to the power 4 plus 5 over 2 x to the power 3 minus 11 over 4 x to the power 2 minus 20 over 2, which is 10x, and plus 12 over 2, 6. You see, we obtain the previous equation. We obtain this equation. This is the one. This is the one which is divided by 2. So we have 1 as the coefficient of x to the power 4. It is the same equation. And when we multiply by 2 this equation, we obtain this one. This is the same. This is the same equation though. So when we divide both sides by 2 and factorize it, we obtain this one: x minus 1 over 2 times x minus 2 times x plus 2 plus x times x plus 3. So all the roots, x minus first root times x minus second root times x minus third root times x minus fourth root. And this gives 0. So we can also, from here, we can, if we already have the factorized equation at hand, we can equate all these parts, all these factors by 0 and obtain the roots as well. But here we have gone the other way around. Otherwise, if the first factor is written as 2x minus 1, which is possible, one obtains the equation that is not divided by 2. Of course, this is possible as well. The third theorem is the most useful one, according to my opinion, because it is easily checked, and it can give us a clue for a root. So theorem 3 says, if in a polynomial equation such as an x to the power n plus an minus 1 times x to the power n minus 1, etc., up to a1 x plus a0 equals 0, a polynomial equation, where an is not necessarily 1. So the sum of all the coefficients, when you sum up all these coefficients, an minus 1, etc., a1, a0, if you obtain 0, then x star equals 1 is a root of this equation. Of course, the proof is simple. When x is 1, replace 1 in this instead of x's. X to the power n is 1 to the power n, 1. X to the power n minus 1 is 1 to the power n minus 1. This is 1 again. All these x to the power something is 1, and x is 1, and a0 is a0. So when all these x and powers of x are 1, what do we obtain? we obtain an times 1 to the power n plus an minus 1 times 1 to the power n minus 1, etc., etc., plus a1 times 1 plus a0. And these ones don't count, so we obtain an plus an minus 1 plus a1 plus a0 equals 0. So if x is a root, x1 star is a root, x star is a root, or x star equals 1 is a root, then you see that the sum of the coefficients are 0, or the sum of the coefficients becomes 0. So when we have a polynomial equation in hand, the first thing to do is to sum up these coefficients. If the sum of all the coefficients of the polynomial is 0, then x star equals 1 is a root, and we can factorize x minus 1 then, and then try to diminish the degree of the polynomial. So here is, well, for today it's enough. We finished our lesson. There are also some exercises belonging to this sections. I will add them to the PowerPoints and share them with you. But at our eCampus page, or our eCampus page, and you have the records, the previous records of this lesson in Turkish in my YouTube channel, Taylan Zafer Bali, and I will put also this record in my YouTube channel, and I will also I will put it at the eCampus site, the link. So thank you for today, and have a nice week. Bye bye. I stopped the record recording.